So here we've got a block of iron of known size, 3 kilograms, and also it starts off at 500 degrees Celsius. And we're going to be investigating what happens if we place that hot iron into a vat of icy water, half solid, half liquid, but with different amounts of water. So if we have 1,000 kilograms of icy slush, or 0.01 kilograms of icy slush, or 1 kilogram of icy slush. So starting with the 1,000 kilograms of water, if we have a very large amount of icy water, so you have a brick of red hot iron, 3 kilograms. Three kilograms of iron at temperature initially equals 500 degrees Celsius. And we're putting that into this vat of slushy water. At 0 degrees Celsius. And how do we know it's got to be at 0 degrees Celsius specifically?
Because it's in between energy, like phases, so it has to be at 0 degrees.
Yeah, that mixed phase, half solid, half liquid, or even just part solid, part liquid, has to be at the phase change temperature, the melting point of water in this case. And so we put these together, and what would you expect to happen? First of all, what's going to happen to the iron?
The iron's going to lose temperature.
Right. Iron temperature decreases, cools off, because it's going to be losing energy. Heat's going to flow as usual from the hot object to the cold object. And meanwhile, what's going to happen to the ice water slush?
Some of the ice water is going to be, it's going to become more liquid.
Yeah, we know at least some of the ice is going to melt. What happens if there's enough energy to melt all of the ice? What's any extra energy beyond that going to do?
And the liquid is going to go up in temperature.
Yeah, maybe it all melts and then increases in temperature. And it could hypothetically increase in temperature up to how much?
(500 degrees Celsius).
Possibly as high as 500 degrees Celsius. But in order to do that, it can't get that hot as a liquid. What would it have to do first?
Turn into a gas.
Right. So it might heat up all the way to the boiling point, 100 degrees, and start to change phase again. So maybe it reaches 100 degrees and starts boiling. And maybe it even completely boils. We don't really know yet. Maybe it partially boils, maybe it completely boils and warms up further. Maybe it all boils away and continues to heat up. So these are all possibilities. We know for sure that the iron's temperature is going to decrease. We know for sure that at least some of the ice is going to melt. Beyond that, we're not really sure. Maybe it all melts. Maybe it starts increasing in temperature after it finishes melting. Maybe it gets all the way to 100 degrees and starts boiling. Maybe it completely boils, like it all turns to steam and continues to heat up in the gas phase. But we don't know about those maybes yet. But it's good to at least explore those possibilities. What could happen, even if we don't know for sure what will happen yet. Any questions on those possibilities so far? And in parts A and B, or actually all three of these, A, B, and C, I'm providing a specific amount of icy water, 1,000 kilograms or 0.01 kilograms or 1 kilogram. The first two of those are kind of extreme amounts. 1,000 kilograms, that's a huge amount of icy water compared to the 3 kilograms of iron. In that case, if you've got an enormous amount of icy water, which of these maybes do you expect is going to happen? Or what would you expect the end result to be if you have a colossally huge amount of icy water compared to a little bit of iron?
Very little change in the ice.
Yeah, that ice is hardly going to change at all. Maybe a little bit melts, but definitely not all of it. And meanwhile, what's going to happen to the iron?
Iron will lose thermal energy.
Iron is going to, sorry, what was that? Yeah, the iron is definitely going to decrease in temperature. How much would you expect it to decrease in temperature? 300? What would you expect the final temperature of the iron to be? Yeah, that's going to have to drop all 500 degrees down to 0 degrees. Because if we know that the water doesn't completely melt, what's the final temperature of the water? Yeah, it's got to be at 0 degrees. The ice is only going to melt a little bit because 3 kilograms of iron compared to 1,000 kilograms of icy water, it's going to take a lot of energy to melt all the ice. So the 3 kilograms of iron probably is not going to be able to provide enough. Ice only melts a little bit and remains at 0 degrees Celsius. Iron cools off to 0 degrees Celsius. So we can expect that there's iron goes all the way down to 0. The ice only melts a little tiny bit. We could even figure out how much ice melts by setting up what equation? What would be our equation here if we know that these are the only changes happening? If the ice is melting a little bit, what kind of energy change is that? Yeah, that would be a change in bond energy for the ice because the ice is in the process of a phase change. And it's only changing phase, so we'd only have delta E bond for the water. Meanwhile, what's happening to the iron? Yeah, the iron's going to be changing its thermal energy because it's going through a temperature change. So we'd have a delta thermal energy for the iron. And what should we expect those changes to add up to? Yeah, we can treat this as a closed system because it's in this insulated vat, insulated container. Presumably the iron and the icy water are only interacting with each other. So we've got a change in E bond as the ice partially melts, a change in thermal energy as the iron cools off. That positive change plus that negative change, the increase and the decrease, have to add up to 0 because it's a closed system. And we can now fill in formulas. What's our usual formula for bond energy or delta bond energy? Yeah, delta mass times the latent heat. And for thermal energy change, yeah, mass times specific heat times change in temperature. So those have to add up to 0. And we can fill in some values there. First of all, what of these are we actually trying to find? What's our unknown here that's our goal? Yeah, we want to know how much mass is, or how much of the ice is changing phase, how much mass of ice we have left versus how much liquid water. We actually know the final temperature here because what temperature is everything going to reach in this case? Yeah, we know everything's going to cool, or the iron's going to cool off to 0. The icy water stays at 0. It's just some of it melts. So we're ultimately going to try to find the delta M. And we don't really even need to fill in delta M as final minus initial here. We can just treat delta M as the variable we're trying to solve for. In fact, if you isolate delta M here, what would you need to do algebraically to isolate delta M before we even fill in any values? Yeah, we want to get rid of this MC delta T, so we'd subtract MC delta T from both sides of the equation. Right, and then divide by delta H. And be careful to understand which terms go with which quantities. The M, the C, and the delta T are all for iron. versus the delta E, the delta H is for water. So it's a good idea to label those. So we've got MC delta T for iron and delta H for water. We actually don't, we haven't specified yet whether delta M is positive or not. Delta M might be positive or might be negative. It should show up in the algebra as we fill in values here. And yes, actually we would expect the temperature of the water would not change at all. It's not just that it changes a little bit, it's that it doesn't change at all. The icy water is going through a phase change, and we should expect that during a phase change, the substance is not changing temperature. It's icy water at 0 degrees, it partially melts, and then it's going to be still icy water at 0 degrees. It's just more liquid and less solid, but it's still at 0. The large amount is how we can expect that it's not going to completely melt. But in general, it's not going to start increasing temperature until it completely melts. So even if it was a smaller amount of icy water, we would expect it to remain at 0 degrees while it's in the process of melting. And then if it completely melts, if it finishes the phase change and continues to gain more energy, then it's going to increase in temperature. But in general, we should expect it to remain at the phase change temperature, in this case, 0 degrees, while it's going through the phase change, and not change its temperature until it finishes the phase change. It's only going to change one of those at a time. Any other questions on the setup of that so far? So let's see if we can fill in some values here. Now that we've written out the equation and isolated delta M, and generally I think it's often a good idea to write out the equation in terms of variables, solve it in terms of variables, and then plug in the numbers at the very end. It's not always practical, but in many cases, it's very useful because it gives you not just a single number, but a formula as the result. So if we wanted to, we could now use other values other than just the ones given in the problem and solve similar problems with the same formula. But let's fill these in. We know negative mass of the iron was given as 3 kilograms. So negative 3 kilograms times, and then specific heat of iron. Where can we get that information? Where do we usually get information about specific heat of a material? Yeah, if we take a look on this data table here, solid iron has a specific heat of 0.45 kilojoules per kilogram Kelvin. So we'll fill that in. 0.45 kilojoules per kilogram Kelvin. And then delta temperature, what are we expecting the delta temperature of the iron to be? It starts at 500 and ends at what? Yeah, it goes from 500 to 0. So what's the delta temperature there? Yeah, direction matters here. It is going to be negative 500 because it's cooling down. You can also see that as final minus initial. The iron starts at 500 and ends at 0. So final minus initial would be 0 minus 500, which is negative 500. And since it's a delta temperature, it doesn't matter whether we call that Celsius or Kelvin. So we can just call that negative 500 kelvins. Since decreasing temperature by 500 degrees Celsius is the same as decreasing temperature by 500 kelvins. Then we'll also need to divide that by delta H for water, which we can also look up in the data table. Specifically, we're talking about the melting process. So we'll use delta H melt, which is 333.5 kilojoules per kilogram. Then we evaluate that. It looks like the negatives are going to cancel out. And we punch those values into a calculator or an abacus, whatever tool you happen to want to use. So 3 times 0.45 times 500 divided by 333.5. And I'm getting about 2. Positive 2. And what are the units of measurement left here? When we reduce everything, what remains? Yeah, it should be kilograms. I mean, we should certainly expect kilograms because this is a mass. It's a good idea to verify that by reducing the units of measurement. Like we've got kilograms in the denominator here, kilojoules divided by kilogram Kelvin, and a times Kelvin, so those cancel out. Likewise, we have a kilojoules over kilograms here in the numerator and kilojoules over kilograms in the denominator, so those cancel out. So all that's left is kilograms. So delta M is 2 kilograms, positive 2 kilograms. What does that mean? How would we interpret a delta M value of positive 2 kilograms? The change in mass, specifically 2 kilograms, have changed phase in which direction? From solid to liquid or liquid to solid? Yeah, solid to liquid. Intuitively, I think we should expect that adding hot iron to icy water is going to make the ice melt. It's going to transition from solid to liquid. Also, the fact that delta M is positive, you can interpret delta M as meaning the change in the higher energy state. Comparing solid water and liquid water, which one is the higher energy state? Or the higher energy phase? Yeah, liquid is higher energy than solid. So if delta M is positive, that means we are gaining the higher energy state, gaining liquid. If delta M was negative, that means we'd be losing liquid. So it would be going from liquid to solid. But this delta M of positive 2 means the amount of liquid has increased by 2 kilograms, and likewise the amount of solid has decreased by 2 kilograms. And we started with half and half, presumably 500 kilograms of ice and 500 kilograms of liquid water. So we end up with 2 kilograms less ice, so only 498 kilograms of ice, and 2 kilograms more liquid, so 502 kilograms of liquid. So that'll be the final state here. Everything's now at 0 degrees. We now have 498 kilograms of ice and 502 kilograms of liquid water. So it's a very small change compared to the total amount. It's still pretty close to half and half. There's slightly more liquid and slightly less solid. Any questions on that so far? And let's take a look at part B. Part B is a very similar setup, except in part B, what's different? Yeah, we have a much smaller amount of water. We start with only 0.1 kilograms of icy water. So what difference would that make? What would you expect to happen conceptually if you take 3 kilograms of iron and then just a very tiny bit of water attached, dribbled on, icy water dribbled onto it? Well, in order for the ice to gain thermal energy, what has to happen first? I mean, without even describing in terms of energies, conceptually, what would you expect to happen to the water? Yeah, it's going to melt, and specifically how much of it is going to melt. Going back to the maybes here, we know the iron's temperature is going to decrease. And we know the ice, at least some of the ice is going to melt. But specifically, if we've got a very tiny amount of icy slush, how much of it would you expect to melt? Probably all of it, yeah, because we've got such a small amount. So that means it's all going to melt and increase in temperature. And again, since there's so much iron and just a little tiny bit of water, presumably it's all going to reach 100 degrees and start boiling, and presumably all boil away and continue to heat up as steam all the way up to what final temperature would you expect here? Yeah, I'd expect it to go all the way up to 500 degrees. Because if we have such a tiny amount of water, it's hardly going to change the iron at all. The iron's going to stay almost at 500 degrees, maybe cool down a tiny bit. The watery icy slush is going to completely melt, warm up all the way to 100 degrees, completely boil, and then warm up as steam all the way to maybe 499 degrees or something. So we should now expect all of these maybes to happen. So in that case, our conservation of energy equation is going to involve a lot more terms. We're going to have a delta E thermal of the iron cooling off. But also we're going to have several changes for the H2O. What changes would we expect here? What changes in energy would we need to include for the water? If all of these things are happening, if it's completely melting and warming up and completely boiling and warming up further, that's 4 changes. So we're going to need, four terms. We're going to need a delta E bond for the melting process, a delta E thermal for the liquid water, and also a delta E bond for the boiling process, because that's a separate phase change. And also a delta E thermal for the gaseous water, the steam. So we're going to need all 4 of these terms: delta E bond for the water as it's in the process of melting, and delta E thermal for the liquid water warming up, and delta E bond for the liquid water boiling to become a gas, and delta thermal energy for the gaseous water, the steam, as it warms up further. And I find it's actually useful to look at this on a 3-phase diagram. If we consider a 3-phase diagram for the water, where do we start on this 3-phase diagram? (0°C), so that's on this phase change bar, and specifically where on that phase change bar? It doesn't start off as all solid though. It starts off where? Yeah, right in the middle, because we were assuming half solid, half liquid. So actually exactly in the middle. And then it's going to be gaining energy up to what final state? Where are we expecting? Yeah, gas, and specifically pretty hot gas. Yeah, 500 degrees. So we're going from initial to final. And if you take a look at the transitions here, we're going from initial to here, and then to here, and then to here, and then to here. Each one of those lines, the horizontal, the diagonal, the next horizontal, the next diagonal, each of those separate lines needs a separate delta E term. We've got delta E bond for the melting process, delta E thermal for the liquid warming up, delta E bond for the boiling process, and delta E thermal for the gas warming up. So it's often useful to draw an energy interaction diagram, like especially if you're not sure which terms you need to include in your equation. Draw out an a 3-phase diagram, mark initial and final, and trace out what path you're taking to get from initial to final. Each one of those bars on the graph, whether horizontal or diagonal, needs its own separate delta E term. Delta E bond for any horizontal, delta E thermal for any diagonal. And we could also draw a 3-phase diagram for the iron, but that's just going to be a diagonal line because it's only changing temperature. Any questions on the equation and how it's related to the graph so far? And again, this is a closed system. It's in an insulated container. So we should assume these changes add up to 0. And in order to write out the values here, or the equations, we've got an MC delta T for iron, delta M delta H for ice melting, and an MC delta T for the liquid water warming up, and another delta M delta H for the water boiling, and another MC delta T for the gaseous water warming up. And again, it's a good idea to label all of those. We've got MC delta T for iron, delta M delta H for the melting process, MC delta T for the liquid water, delta M delta H for the boiling process, and MC delta T for the gaseous water. So label all of those to make sure with subscripts or underwriting to make sure you're keeping track of which one goes with which which substance and which phase. And of those, what's our main unknown here? What don't we know? What's the missing information we're trying to solve for? Because all of the constants, well, delta M, how much of the ice are we assuming is melting? Yeah, we're assuming all of it's melting. And how much of the liquid water are we assuming is boiling? Also all of it. So we can write out those delta M's. The delta M, for instance, we started with only half of it being ice, so 0.05. So delta M, since we're going from 0.05 amount of liquid to 0.005 liquid to 0.01 liquid, that's an increase of 0.005. So delta M is going to be 0.005 kilograms for the melting process. For the boiling process, we start with 0.01 kilograms of liquid and it turns into 0.01 kilograms of gas. So delta M is going to be 0.01 kilograms. Because we have 0.005 kilograms of ice turning into liquid. And then by the end, we have 0.01 kilograms of liquid turning into a gas. So we know both delta M's. And likewise, M, the amount of liquid that's warming up is 0.01 kilograms. The amount of gaseous steam that's warming up is also 0.01 kilograms. And the amount of iron warming up is 3 kilograms. So we know all the M's and delta M's. We can look up all the specific heats and latent heats of melting and boiling on the data table. So what's really the only unknown left here? Yeah, we don't know the final temperature this reaches. So what we're going to need to do is treat final temperature as an unknown variable. We at least know that everything reaches the same final temperature though. So let's try writing out each of these T finals and see what those are going to look like. For example, write out each of these delta T's. Delta T for the iron, final temperature we don't know, but what's the initial temperature? Yeah. So for the iron, this term, MC delta T for the iron, delta T is going to be T final minus 500 degrees. And likewise for the liquid water, if we're taking a look at the liquid water warming up term, delta E thermal for the liquid water, what temperature does the liquid water start at and what temperature does the liquid water end at? Yeah, the liquid water starts at 0, but only goes up to 100 because after that, it's no longer a liquid. So for the liquid water's thermal energy term, we would have 100 degrees Celsius minus 0 degrees Celsius. And then for the gaseous water, that starts at what? Yeah, that starts at 100 and ends at some unknown final temperature. It doesn't go all the way to 500. It'll go to close to 500, but remember the iron does cool off a little bit. So the water isn't going to go to the original temperature of the iron. Instead, the iron and the water are going to go to the same final temperature, which we should expect to be slightly less than 500. So the delta temperature terms are going to be written out like this. For the iron, it starts at 500 and goes to T final. For the liquid water, it starts at 0 and goes to 100. Then the gaseous water starts at 1 or picks up at 100 where the liquid water left off and goes up to some unknown T final. So T final is the only unknown in this equation. It does show up twice. T final is going to show up twice in the equation, but it's the same value T final. So you really only have one unknown variable. So what I would do here, fill in all the numbers, simplify as much as possible, distribute any multipliers, combine like terms. You ultimately should end up with something times T final plus something equals 0. And then you can isolate T final algebraically. Any other questions on that so far? And I don't think we're going to have time to go through the algebra here, but try this out. Write down this equation, fill in the numbers, solve for the last unknown T final, and see what you can do with that. But I'd like to take a look at part C also, because C is going to be a little different. For C, we're going to have to be a little more careful here, because instead of having a colossally huge amount of water compared to the iron, or a ridiculously tiny amount of water compared to the iron, we now have a more reasonable amount of water. We have an amount of water that is much more comparable to the iron itself. So we're going to have to be a little more careful there. Specifically, if we've got 1 kilogram of icy water, so a more reasonable quantity. Less water than there is iron, but still pretty close. Close enough, we got to be careful about it. So if we again take a look at these maybes, we know for sure that the iron's temperature is going to decrease. We know for sure that at least some of the ice is going to melt. But we can't really go further yet. We don't know just from looking at it whether all the ice melts or only some of the ice melts. So we got to figure out, does this act more like the 1,000 kilogram situation or more like the 0.01 kilogram situation? Because it's somewhere in between those. We got to figure out, does the ice all melt before the iron cools down to 0? Or does the iron cool down all the way to 0 before the ice all melts? So let's check both of those possibilities. We got to check those maybes. Maybe the ice all melts, or maybe the iron cools to 0 degrees Celsius. And we want to figure out which one of those maybes actually happens. So for each one of those, maybe the ice all melts. What kind of energy transition is that? Yeah, that's delta E bond. So we can use our usual delta M, delta H. So that'll be delta M. If we're assuming that all the ice melts, how much delta M is that? Remember though, it didn't start off all ice, it was only half ice. So if the 1 kilogram is half ice and half liquid, yeah, delta M will just be 0.5. And then delta H for water melting is still 333.5 kilojoules per kilogram. So multiply those and we'll get half of 333.5, which is what, 166, I think. Double check that. Yeah, 166.75. So that means that the ice, in order for the ice to completely melt, it has to gain 166.75 kilojoules, about 167. So that's what has to happen in order for the ice to completely melt. Meanwhile, we're assuming the iron might cool down all the way to 0. That would be a change in thermal energy, so MC delta T. And if we fill in those values, mass of iron, 3 kilograms, specific heat of iron, what was that? 0.45. And then delta temperature, if we assume for the purpose of the maybe, the hypothetical, that it's cooling all the way down to 0, that'll be negative 500 Kelvin. So multiply those together. I think we did that already in the previous one, right? 3 times 0.45 times 500 was 675. So negative 675 kilojoules. So in order for the iron to cool off all the way to 0, it has to lose 675 kilojoules of energy. In order for the ice to all melt, it has to gain 167 kilojoules of energy. Which one of those processes is going to finish happening first? Yeah, the ice is going to finish melting long before the iron cools down all the way to 0. Because keep in mind, these are exchanging energy at equal rates. If the ice gains 1 kilojoule, the iron loses 1 kilojoule in the same amount of time. If the ice gains 167 kilojoules, which is enough to melt it, then the iron in the same amount of time loses the same 167 kilojoules, which is not enough to cool it down all the way to 0. So the ice does finish melting long before the iron cools all the way to 0, which means we can confirm that maybe. Maybe it all melts? Yes, it does all melt. And then there's energy left over. The iron is capable of contributing more than enough energy to melt all the ice. So we know, yes, the ice all melts. And that means if it's all melting, what's the next thing the now liquid water is going to do? If the ice all melts and then that liquid water still continues to gain more energy, what's the liquid going to do? The iron's going to cool down. And meanwhile, what's the liquid water going to do? It might turn into a gas, but it can't turn into a gas yet. What would it have to do first? What's the next transition that's going to happen after it finishes melting? Yeah, it's going to increase in temperature. The next maybe is maybe it gets all the way to 100 degrees. We don't know yet how hot it's going to get. Maybe it gets all the way to 100 degrees. Maybe it stops somewhere in between. So that's our next maybe. We're next going to investigate maybe the liquid water warms up all the way to 100 degrees Celsius. And we want to compare that to the iron. We now find that the iron doesn't cool down all the way to 0. Instead, we should check maybe the iron cools down to, let's say, that same temperature. Because we now want to know, does the new liquid water, now that we know it all melts, does that liquid water get all the way up to 100 degrees first, or does the iron cool down to 100 degrees first? Because if the liquid water does get to 100 degrees first, then it's also going to start boiling before the iron gets there. But we need to check both of these. Maybe the liquid water warms up to 100 degrees, or maybe the iron cools down to 100 degrees. So we need to check both of those and see which one of those finishes first. Which one gets to the next transition first. So liquid water warming up to 100 degrees, that'll be a delta E thermal again. So we'd have, and now we're talking about all the liquid water. So we now have a full 1 kilogram times specific heat of liquid water, 4.18 kilojoules per kilogram Kelvin. And we're assuming it's increasing in temperature from 0 to 100. So that'll be positive 100 Kelvin. 1 times 4.18 times 100 will be 418 kilojoules. So that means it's going to require 418 kilojoules of energy to raise the water all the way up to 100. Meanwhile, if we take a look at the iron cooling to 100, that's also a delta E thermal. We're assuming we've got 3 kilograms as the mass. Specific heat is still 0.45 kilojoules per kilogram Kelvin. But now what would be the assumed delta temperature for this hypothetical? We're saying, what if the iron cools down from 500 degrees down to what? Down to 100. So if delta temperature, final minus initial, would be 100 minus 500. So that'll be negative 400 Kelvin. Multiplying those together, 3 times 0.45 times 400 is negative 540. So that means to warm up the liquid water to 100 takes 418 kilojoules. To cool off the iron to 100, it would be losing 540 kilojoules. But we got to keep in mind, we're not just adding 418 kilojoules to warm up the liquid water. How much water did we, or how much energy did we already have to add to that before we could even start warming up the liquid water? Yeah, we had to add the 167 kilojoules first. So we should really be combining those. Combine all the energy we're saying the water has gained so far and compare that to the energy the iron loses to cool down to 100. So 166.75 plus 418 is about 584. So that means in order to melt the ice and warm up the liquid to 100 would cost 584.75 kilojoules. As the iron cools off to 100, it can contribute up to 540 kilojoules. So which one of those processes finishes first? Does the ice melt and warm up to 584 or warm up to 100 first? Or does the iron cool down to 100 first? Which one of those processes overall requires less energy? Keep in mind though, we're combining these. In order to melt and warm up to 100 degrees, you'd have to add 585 kilojoules. For the iron cooling off to 100, it can only contribute 540 kilojoules. And 540 is smaller than 585. So that means that the iron actually does finish cooling off to 100 degrees first. It won't get down to 0. We already found that it doesn't get down to 0. But it is able to get down to 100 degrees because the iron cooling off to 100 degrees contributes 540 kilojoules of energy. But as the ice gains 584 or 540 kilojoules, 540 is enough to completely melt it, but is not enough to melt it and warm it up all the way to 100 degrees. So that means the water does not reach 100 degrees Celsius because the iron can't contribute enough energy to make that happen. So it does not reach 100 degrees, does not start boiling, and we can ignore everything beyond that as well. We know that the liquid water, the ice water does melt completely. The liquid water does warm up, but not all the way to 100 degrees because the iron cools off to 100 degrees first. And at this point, we can now actually set up a conservation of energy equation because we know that there's going to be no further phase changes. Since the liquid water doesn't get to 100 degrees and the iron does cool down to 100 degrees, that means they're going to continue changing temperature and meet somewhere in between. So the final temperature is going to be somewhere less than 100 degrees. The water is going to be all liquid. The iron is going to be all solid. So we should now be able to set up the equation. We know we have a delta E bond of the water melting. We know we have a delta E thermal of the water partially warming up. And we also have a delta E thermal of the iron cooling down. And we know those are the only changes that are going to happen because the liquid water doesn't get all the way to 100 degrees. Any questions on that so far? And some of the calculations here we've already done. Delta E bond, we're talking about all the ice melting. We already calculated the ice all melting costs 166.75 kilojoules. So we can actually fill that in. We don't need to fill in a formula again. We can just fill in the value we already calculated. For the liquid water melting though, or sorry, the liquid water warming up, we can't actually use the 418 because the 418 was if it gets all the way to 100, and we just found it doesn't get all the way to 100. So for the delta E thermal of the liquid water, we'd fill in MC delta T for the liquid water. Likewise, for the iron, we know it cools down all the way to 100 and beyond. So we shouldn't use the negative 540. We should write out another MC delta T. So fill in the mass of the liquid water, 1 kilogram, mass of the solid iron, 3 kilograms, the specific heat for each one of those. And for delta T, each one of those would be either T final minus 0 or T final minus 500. But again, it's the same T final, so you can solve for that one unknown. And you should end up with some temperature a little lower than 100 degrees because we found that the iron does cool down to 100 degrees and keeps cooling off. Any other questions on that approaching equilibrium idea? The idea of these substances racing to get towards equilibrium and looking at each step in the process to see which gets there first. All right, then try out some other examples. Let me know if you have any other questions, and I will see you next time. You're welcome.